Hey everyone. So in this video, we're covering density, and the question that I have to start off with is, why do salad dressing labels tell you to shake the bottle before use? If you've ever seen a salad dressing bottle before, you know that the olive oil and the vinegar are separated. And the reason why is because they have different densities. And so that causes the olive oil to float while the vinegar, which is a little bit more dense, to sink to the bottom. So that's a general picture that you would see for some kind of a vinaigrette. The reason why I wanted to cover density now is because it is the core of earth science. There are so many different units where density is very applicable, whether that's meteorology, which we're moving into next, oceanography, even astronomy, believe it or not, as well as plate tectonics, geology, which covers your rocks and minerals. So it's very important. And I know a lot of you probably know a decent amount about density, but it's always good to go over because we are going to be talking about it for the rest of the year. So density is a property of matter. And what I mean by that, it's basically a characteristic. So for example, water has a density of 1.0 or 1.0 grams per milliliter. And because density is a property of matter, and therefore this 1.0 grams per milliliter is a property of water, it doesn't matter if I have a small cup of water or a gigantic pool of water. As long as it's pure water, its density will be the same because it's a characteristic of water. All substances have densities, and usually those densities are different. So, what density is a measure of compactness. I like to think about it like two suitcases. If you have the same exact suitcase or boxes, they're the same size, same shape, everything, same volume. But one has a different amount of stuff in it compared to something else, or the other one. Like you see here, this picture. I should just be referencing this picture. Then you can tell, well, the one that, even though the two boxes are the same size, the one that has less stuff in it is going to be less dense. There's more room in there for things to spread out. Meanwhile, the other box, same shape, same size, that has, or it has a lot more materials in it, so we consider it more dense. You can actually taste this difference too. Something like a pound cake. If you've ever eaten a pound cake before, it's really dense. It absorbs juices really well because it is dense and doesn't get soggy quickly. But something like sponge cake will be a lot lighter, a lot fluffier. It's going to get soggy really quickly because those juices can just percolate through very quickly. So you can taste the difference, you can feel the difference. Usually you can't see the difference unless you see those air holes in there. But the formula for density is mass over volume because density is a ratio between the amount of matter or the amount of mass as well as the space that the item takes up, so the volume. I like to remember this formula, mass divided by volume, because we love density. It's the core of earth science. And the top of the heart, because we love density, that top of the heart looks kind of like an M, and the bottom of the heart looks kind of like a V. So it creates this heart shape because we love density. And why I'm trying to teach you that now is because, granted, I just know someone is going to, on a test, want to divide volume or want to do volume divided by mass, but flip it, it's mass divided by volume. You could also think mountains over valleys. Mountains are tall, they're high, they're above. Valleys are low, so they're below. There's a few different ways, but density equals mass divided by volume. Let me move this a little lower. Okay. Oops. Because the formula is mass divided by volume, and we use the metric system in earth science, our units are either going to be grams divided by centimeters cubed for solids or grams divided by milliliters for liquids. The difference between these two really just comes about with the how you're finding volume, because you can find volume using the length times width times height formula, which you would use the length unit meters for, or centimeters. Or you could find volume using increments on the side of a beaker or a graduated cylinder. And those liquid measurements are measured in liters or milliliters. So they're equivalent to each other. There's really no difference. It just basically describes the object itself. If you see centimeters cubed, you know that it's probably a solid. And if you see milliliters, you know it's probably a liquid or an irregular solid, which we'll get to in a second. Irregularly shaped solid. Sorry. The bell's going to go off in a minute, so that might disrupt again. So you might already know this, but if not, when it comes to earth science, like I said before, we use the metric system. That is more universal. So if we go to share our data with other parts of the world, they generally will be using metric systems. So it just keeps things nice and square and even. A lot of places don't use inches and feet and yards and pounds and ounces and so on. So we use what's globally accepted, which is the metric system. And for mass, which another word for that is weight, not quite the same thing, but for mass, the unit that we're going to use are grams, which is abbreviated little g. You can use a triple beam balance, which I've pictured here. Oops, gosh, which I've pictured here. You can use one of those in class, though. In class, though, we use just a normal kitchen style scale that's electric, so it's a little easier to use. Either way, you're measuring the weight or the mass, rather, of that object. Meters is what's used for length, so just like a normal ruler has both inches and centimeters on it, we're going to use the metric side, so the centimeter side. Now, if you use the volume formula, length times width times height, you're multiplying three different numbers together to get your volume, but you also multiply your units together as well. So centimeters times centimeters times centimeters. When you multiply three of the same unit together, you get that unit cubed. So that's why you hear centimeters cubed when talking about volume. That's why you hear centimeters squared, for example, when talking about, area or whatnot. And I think just normal centimeters for perimeter. I got to double check though, because that's just addition. So anyways, moving on though, this isn't math class. For liquid volume, as well as irregularly shaped solids, you would use liters, which is, think like gallons, but it's not a gallon. For reference, 1 liter is approximately half the size of a soda bottle. So that's what a liter is. And we really could use any type of measuring cup. Here you could use a graduated cylinder, a beaker, Erlenmeyer flask. We primarily use graduated cylinders though. Okay. Some of you may know this already. In case you don't know, though, here's the information. So within the metric system has base units, and then depending on what you're measuring, you might want to use a larger version of that base unit or a smaller unit or version of that base unit. So it's kind of like French fries. You can get small fries, you can get large fries. The large, small, medium describes the amount, but they're all fries. So same thing here. Our base unit is right in the middle. You could do meters again for length, liters for liquid measurement, volume, or grams for mass. So those are our base units. If I'm measuring the length of a car, for example, meters would be an appropriate unit to use for length. Because maybe a car is equivalent to like 2 meters, right? That works. But if I was measuring the distance from here to Strasbourg, that would be a lot of meters, and my number might be really long. I mean, we could even keep going if you want to talk about distances in space. Those are really big numbers. And sometimes it's, I don't want to say annoying to use the big numbers, but it can muddy up your paper when you have really, really, really big numbers. So instead, what a lot of people do is they just up the size of that meter, just like you can upgrade your fry from a medium to a large. And I think at McDonald's you even have super size or something. So if you are measuring really far distances, you would measure using kilometers or kilometers. So a kilo is 1,000 of your base units. So if I'm measuring in meters, but I want a bigger version of meters, I would add that kilo in front because that's saying, okay, well, a kilo is 1,000. So 1,000 meters is a kilometer. And now instead of saying that, I don't know, Strasbourg is 5,000 kilometer or meters away, I'm actually not quite sure how far it is. Now you can say it's 5 kilometers away instead. So that number gets smaller because the size of the unit gets bigger. So it just can help when doing some math or just communicating information, makes it a little nicer. I think a better example though is when you go smaller towards something like centi or milli. So you've probably heard of centimeter before and millimeter before. A centimeter is 1/100th of a meter, and a milli is 1/1000th of a meter if you're using millimeter. Those are really great for trying to measure like your thumb or the length of a paper clip, just things that are very, very small. Because otherwise, you'd be, if you used a meter, you'd say, well, this is 0.00125, whatever the number is. And that can get, again, kind of confusing. So we just use the appropriate size according to the object that we're trying to measure. Because these are prefixes, meaning they go in front of the word or in front of the base, you can add this to any of your base unit. So kilometer or kilometer, centimeters, millimeter, all describes different sizes of length. You can do the same thing with liter and gram, kiloliter, centiliter, or milliliter. We primarily just use milliliter though in here, or kiloliter, but gram, kilogram, centigram, milligram. We don't use deci, deca, or hecto. Those are just kind of uncommon sizes. They are a thing, but they're just kind of uncommon. So each, I call them steps, each step increases or decreases by 10 as you go up or down from the base. There, you can actually go larger. This is where you're on your computer, you have a certain amount of bytes of storage. A byte is actually a base unit. It's just not common to talk about for a science class. But your gigabyte, your terabyte, I know there's another one, megabyte. Oh, I think mega might be million. I had a question today about that. Those are sizes above kilos. So a megabyte, gigabyte, terabyte. I think tera is the largest. Those all describe different amounts of storage that you have. So that I think a lot of people maybe can connect with more because of just doing a lot with computers these days. All right. Excuse me. So real quick, for the lab in class, you're going to have to read a graduated cylinder. And on the graduated cylinder, this is how you do it. Fill it up, obviously. And then I want you to get down to eye level with it. I want you to put it on a flat surface because otherwise it could be tilting towards you and your data could be skewed. You might be reading the wrong number because it's tilted. So put it on something flat. Then you're going to get to eye level so that way you're not reading at the wrong angle because that can also mess up your data. And you're going to read the bottom of the meniscus, which is this curve that the water makes. Makes this because of, I was calling it cohesion or adhesion. Someone today said it was capillary action. They're probably right. It's been a bit since I've studied properties of water. But either way, you're going to read the bottom of the meniscus because water likes to climb up things like on a paper towel. If you've ever dipped paper towel in water, you can see it slowly climbing up that paper towel. Same thing with the sides of a graduated cylinder. It will climb up the sides of it. So that's going to give you inaccurate data. So you should always read the bottom of that curve. What else with this one? There were some specific notes that I made mention of for the lab. I'm just going to skip that for this video though. And I might make a separate video on how to do the lab. But those are the three things. Get it on a flat surface, get down to eye level, read the bottom of the meniscus. Now, I was mentioning before that we use milliliters which is the units on a graduated cylinder because it's liquid volume. We use milliliters for irregularly shaped objects because they're very hard to measure with a ruler. I wouldn't be able to get a ruler to this toy dinosaur and measure it accurately. I could get a estimate, but my estimate would be pretty far off because look at all this negative space between the legs, between the head or underneath the head itself. It's all round. The tail, a lot of negative space, which means that if I'm accounting for that in the volume, I would be off. So, how you're going to measure something that is irregularly shaped is you're going to use what's called the water displacement method. I like to relate this to trying to find the weight of your pet. If you have a pet at home and you need to give them medicine, you need to know how much medicine so that way you don't give them too much or too little. And they usually on the bottle of the medicine or flea and tick, whatever, it'll tell you for your dog's weight, this is how much they should take. So you have to find their weight. Well, I don't know about you, my dog doesn't like to sit on the scale. So what I have to do is I have to step on the scale just by myself, weigh myself, step off the scale, pick up the dog, step back on the scale, and find our combined weight. Because I know what I already weigh and what I'm looking at is our combined weight, I can subtract my weight from our combined to get just the dog's weight. So I'm able to do weight displacement. Water displacement is the same thing. How much water is displaced when you put the object in the graduated cylinder? So what you're going to do is you're going to fill up your graduated cylinder to any line. It doesn't matter. You could just turn it off and again, read it just like you would. Find what the value of your initial reading is by, again, looking at the bottom of the meniscus. Since the interval here is 0.2, I was going to say 2, 0.2, this initial volume would be 5.8. This is something weird about graduated cylinders. Sometimes the label for the line is written on the top, on the bottom, on the side. In this case, it's listed on the bottom. I know it is because see how we have these very long lines every so often, followed by a whole bunch of short lines? The long lines are the ones that are going to be labeled. In this case, the number sits below the label or below the long line, but that's the one that's getting the label. So it just happens to be that the 5 is sitting underneath the long line. I hate how graduated cylinders are labeled, but I think just because they can be so skinny, they sometimes have to do it that way. I've seen the number sitting on top of the line or next to. The fact that this is under, I think, is quite silly. Anyways, our initial reading is 4.8 milliliters. Now I'm going to put the toy dinosaur in. And if you've experienced life before, you know that when you put something in water, the water level rises. So the water level rose. It rose to, here's the 6, 2 below. It rose to 6.6. Oh, I'm sorry, 5.6. I just did a mistake, and that's okay. So 5.6, that's my new volume with the water plus the toy. I didn't put any new water in there. I still have the same amount, but I have the toy. So I'm going to subtract these two values, not together. I'm going to subtract the two. So 5.6 minus 4.8 is 0.8 milliliters. And that is the volume of the toy. So that's how you're going to do water displacement. You're going to look at the new level of water. I had a student that was trying to look at the height of the toy underwater. Don't do that though, because again, same thing. It's as if you're trying to measure the length, width, and height of the dinosaur. You're going to get inaccurate readings, right? Because these first 2 milliliters, it's not all dinosaur. It's dinosaur plus water mixed throughout. So you're just looking at how much the water rose for water displacement. Hopefully that helps. All right, moving on. Density of water. Water has a density of 1.0 grams per milliliter. I think it's so cool how beautiful that number is because it's so plentiful and it's used so widely throughout the world. And of course, it has such a clean, easy to remember number. So we love it. Because of that, it's often used to compare densities because you can tell if something floats in water or sinks. And if something is floating in water, it should have a density less than water. So something less than 1.0 gram per milliliter or 1.0 gram per centimeter, not squared, cubed for solid, regularly shaped objects. Again, the two units are equivalent to each other, so you can interchange them. And if something sinks, it should have a value greater than 1.0 gram per milliliter or gram per centimeter cubed. So of these three, you can tell that aluminum is sinking in the water. It's way below the surface of the water. So it should have a value greater than 1.0 because it has sunk below the surface of water. Wood and cork are both floating in the water, so they should have a density not greater, less than 1.0 because they're floating, and things that float are less dense. If you notice though, cork is floating even more. The majority of it is above water, so it's probably the lightest in density. Wood's probably middle, and aluminum is the highest density. Right. All right. So does size matter when determining density? If you change the size of this Play-Doh ball, for example, will that change the density too? And the answer is no. If you change the size of something, you're also changing the amount of material. For example, if I'm trying to find something I could break in half, I could just do a piece of paper. I'm trying to see if sure, an eraser. Okay. I like these erasers though. But we'll just use it as an example. So if this eraser had a mass of 20 grams and a volume of 10 centimeters cubed, 20 grams for the mass, 10 centimeters cubed for the volume, my density 20 divided by 10 would be 2 grams per centimeter cubed. So if this eraser has a density of 2 grams per centimeter cubed, right? And I cut it in half. So imagine I'm cutting it in half. Not only have I decreased the volume in half, but I've also removed half of the material, the mass. So I've cut both my mass and my volume in half. Should that change my density? Should that make my density be cut in half? Well, if I started with 20 grams of mass and I've cut it in half, I now have 10 grams of mass. If I started with 10 centimeters cubed of volume, then when I cut my eraser in half, now I have 5 centimeters cubed of volume. So my new eraser has 10 grams of mass divided by 5 centimeters cubed of volume. 10 divided by 5 is still 2. So changing the size, changing the shape, changing the amount of mass does not matter, because if you're simply cutting it in half or taking a chunk out of it or whatever, you are not impacting the density, because density is a ratio. So if you change mass, you also change volume, and vice versa. If you're just, doing something like cutting a piece of it. All right. So density does not or is not affected by change in size. That's the big takeaway that I want you to get from this. Remember, that's also going back to it being a characteristic of that substance. Whatever this is, high polymer eraser, whatever the substance's density is, it doesn't matter if I have this size eraser or this one. I really like these erasers. They both have the same density. This one's larger, so its volume is higher, but there's more mass in it too. So the ratio is still the same. This one's smaller but has less mass. Ratio is still the same. All right. The only way you can change density is if you change the temperature. If you change the temperature of a substance, what you're doing is you're expanding or contracting the volume only. You're not changing the mass, you're changing the volume. You're saying, okay, well, I have 20 grams of whatever, that's your matter, how much matter you have, but I'm going to heat it up and things that heat expand. So I'm going to heat it up and those 20 grams of things are going to take up more space than before. So you increase your volume. So let's say I need to write this out. I feel like it'd make sense if I wrote this out for you guys. I did this on the board, but doing this in the computer is different. Okay. So I'm going to show you this in just a second. If my normal volume is, if my normal substance is 20 grams over 20 grams of mass divided by 20 centimeters cubed of volume, I'm going to get a density of 1 gram per centimeter cubed. Okay, so that's my density for something normal, something at a normal temperature, like water, for example. I do want to make a point about air just because the hot air balloon. So obviously this is water's actual density. I've taught this 5 times already, so I'm kind of losing my mind a little bit on what I have said and haven't said. So sorry about that. It's not the cleanest video I've made. But I know that this is water's density, but let's just imagine that we're talking about air for a second because air is really easy to imagine. If you heat up air like in a hot air balloon, what you're doing is because what heat is molecules moving or vibrating at some speed. And the more heat you add, the more those molecules move. So, and the more they want to move apart. Because it's kind of like when if you play sports and you just ran like 50 laps or whatever, you do not want to be in that group circle, that huddle up. Everyone's hot. It's hot outside. Body temperatures are just crazy. Like you don't want to be huddled up because you're already hot and you're already sweating. You just feel uncomfortable. You want to just air out those pits as much as possible, get some breeze flowing through you so you can cool down. And molecules do the same thing. Look at this. Where's my mouse? Look at this here, right? These molecules, they just want to spread out when they're super hot so that way they can cool down. So imagine like this hot air balloon. Imagine you turn on the fire in a hot air balloon and you're now heating up the air. Well, when you heat up the air, it goes from normal distance apart to now wanting to spread out from each other because they're hot. So the volume has increased. You're increasing the volume. And what that does, I'm going to write this down. Let me write this in red to be extra. And I'll get blue as the next one. I can't find red, but I have pink. So if I heat up the air, I know it's not air. I know my formula I did is for water, but just go with it. I still have the same amount of mass, but let's say I still have the same amount of mass, but that mass now takes up more space. I've heated it up so it's expanding and it's taking up more space. I've doubled it just to make it easy to see. So 20 divided by 40, that's going to be 0.5 grams per centimeters cubed. So if you notice the difference, when I heat something up, that changes the volume from, in this scenario, it doubles, and that drops my density. So I have a lower density when heated. That is important. Hot things rise. If I were to cool it down again, and that's why your hot air balloon rises, is because that hot air is captured in the balloon. So the balloon expands but doesn't let the hot air out. So what does it do? Well, its density is less than the surrounding cooler air outside of the balloon. So it floats in the air because, again, its density is less. I want to know who thought of the first hot air balloon. I know that information is out there, but I never go to check. Okay, so now let's say that you're done with your hot air balloon. Maybe you tried to propose to someone. They said no, things got awkward. You want to go back down to land. I don't know. Now we're going to cool it down by turning off the fire. And what happens? Well, all of those really hot molecules start to get cold. They don't move as much. And you know what? They're now kind of cold. They actually want to be really close to each other, and they want to huddle up like penguins. They want to conserve as much body heat as possible. So they're going to get tighter and tighter and tighter, getting really close so they can conserve as much heat. I just want you to have that imagery. Is that actually what's happening? Not exactly, but imagery wise, imagine like a huddle of penguins. They get closer and closer and closer. So your molecules take up a lot less space when cold. So compared to the normal, I'm gonna go smaller. I'm gonna go back to the normal one and go smaller from there. So if at a normal temperature, we take up 20 centimeters cubed of space, maybe now we take up 10, right? We're really cold, 10 centimeters cubed of space. We've really contracted and shrunk, right? 20 divided by 10, that's 2 grams per centimeters cubed. My density is a lot higher, all right? High density when cooled. This is really important. I don't even know if you guys can see this. I'm not even looking at my screen for like myself in this. So maybe, hopefully you can see what I'm writing, but at least you'll have it said. This is a really important concept in earth science because differences in land, differences in how land is heated, whether that is at different altitudes, whether that is the texture of the land, the amount of vegetation versus asphalt, whether that is the biosphere, latitude, land versus water, all of that heats up differently and is therefore going to heat up the air above it. So imagine, if you will, areas of land that are colder, areas of land that are warmer. Now you have temperature differences. That cool air wants to sink, that warm air wants to rise. Because of those differences in densities, we get things like wind patterns. We get things like storms moving in at different areas. We constantly on the news are talking about this warm air coming up and is going to add moisture and will be the perfect conditions for this tornado or that hurricane. We get that because of differences in densities. We have migration routes in the ocean as well as nutrient cycling in the ocean because of ocean differences in temperature between deep ocean and surface ocean, between equatorial ocean and polar ocean. Those differences in temperature create that circulation needed for life to thrive. In our core, in our mantle, we have magma being heated from the core that rises to the surface where it's chilled and sinks back down, creating convection currents in the mantle that create plate tectonics, which leads to your mountain building, your volcanoes, your trenches, your valleys, all of that, earthquakes, all of that is simply due to changes in density. Isn't that crazy? Even how our solar system is organized comes down to differences in density. So, this is something that truly rules our world and is so important to talk about because it's relevant in everything. So, you might think that you know density. You really need to, though, in earth science because you will see this in every single unit, I promise you. You're probably thinking, though, about the one exception to the rule, and that is ice. Ice is as far as I'm aware, the only exception. And again, one of those things I just think is quite beautiful because if ice sunk, right? Ice is cold. We just said cold things sink. Ice is a lot colder than water, so it should sink. If it did sink, though, think about all of the life in water and that surface of the water freezing, like a lake freezing, like it does. You can walk and ice skate on certain lakes. Ponds probably is a better better term. Well, imagine all that ice sinking. It would kill all of the organisms below it, and we would not have aquatic life being sustained, which would lead to very poorly regulated ponds, because aquatic life does a lot to cycle nutrients and keep those waters clean and good for land animals or mammals, whatever. So it's really truly a beautiful thing that it is the exception. And the reason why comes really to the shape that's created when those water molecules are frozen. If you notice this shape, first off, do you see how they see this like Mickey Mouse shape, those two blue atoms and this red atom? That's supposed to be your H2O, two hydrogens and one oxygen atom. That's your water molecule. Now, there's a bond, I'm pretty sure that's what this is trying to show. There's a bond between all these different molecules when it is frozen, and that creates a much bigger structure than the actual water atom itself. So the shape of ice gets a lot bigger, and additionally, this whole area in between is the perfect spot for air to fit in. So we get air captured in our ice along with this bigger shape, which normally doesn't happen, but with other substances, but the shape gets bigger, so volume increases. And now we have this cold substance that actually floats instead of sinks. And it's one of the only exceptions I know of, which is quite cool. So that's why it floats, air getting captured plus the shape. But if you're just talking about water itself, not necessarily ice, cold water sinks and warm water rises. But again, once that cold water gets past the point of freezing, then that ice will float because of the air and the larger volume space. But anyways, that is it for this video. Sorry that it was a little spotty here and there. I try to just do one takes as much as possible. Please let me know if you have any questions. I think I'm also going to take a video of the lab so that way you guys have that. All right, see you later.